Hello, biostatistics class. Today we're going to go over some correlation analysis things. And so, in correlation analysis, hopefully you've looked at the video that Dr. Beckman put together. What we actually do is we look for the degree to which there's an association between two quantitative variables. And I've pulled up the triathlon data set that you've looked at before, because we've got a bunch of quantitative variables and we can think about how we expect things to be associated and use it to illustrate this concept of correlation. And so in correlation, we typically use it when we think that there might be an association between two variables. It's not necessarily causal. Often what we have are descriptive data. And we're going to do this, and let's actually make a little rearrangement first. So once you pull up from your blackboard area the triathlon data, there's one data point I had to remove. Mr. Jones, he didn't have some data entered, so I got rid of him. But ultimately, when I look at this, I've got a lot of pairs of data, X and Y. And if I want to make a graph to kind of look at how things are related, it helps if I have variables that are right next to each other. So I'm actually going to click over here on this G, and I'm going to insert a new column, and it's just going to be this column right over here. And so I am going to say, well, this is also transition time 1. Remember, we've got transition time 1. That's the time it took to go from swimming to bike riding. And I'm just going to move all this data over here. So I copy that 1 over, grab the corner, pull down, and I get lots of data all lined up down there. And so now I have side by side transition time 1 and then transition time 2, where transition time 2 is the amount of time it took to get off the bike, changed, and ready to run. So often when we do the correlation analysis, it's nice to just look at the data, and we use a scatter plot to do this. So in a scatter plot, we basically want to highlight our data. So I'm going to highlight my T1 and T2 data. And then I'm going to do insert and go over here, and you can see insert a scatter plot. I don't want any lines here right now. I just want these data. So I've made this a little earlier. I'm going to take the chart I just made, whoop, and move it down here a little bit so you can get a better look at it. And so this is what our data look like. I'm going to make it a little bigger. Whoop. And if you look at this, you can see there's a tendency for, as T1, which is on the x-axis, to get bigger. T2 also gets bigger, but there's a lot of scatter. And so to help visualize what's going on, we can fit a straight line to it. And if I do a right click on one of these data points, or I can go over here and go to the plus, I can say trend line. I'm going to add a trend line, and I want more options. And on these options, I want it to be linear, straight. You can also do fancy things like polynomial lines if you wanted to. But we're going to go down here, and I want to see the equation on the chart and also r squared on the chart. I'll move that up where you can see it. And so make sure you understand what r is, and we're going to calculate r. So if we know r squared is equal to 0.3006, then R is going to be equal to the SQRT, the square root of that value. Now remember, when you take a square root, there's actually a positive and a negative root. And so the square root here is either 0.54827 or negative 0.54827. And the question is, which is it? Well, because this is a positive correlation, because this line trends upward, that means that you have a positive correlation and that we want the positive root. And so R here is going to be equal to 0.54827. And so you should keep that in mind. So we've plotted lots of data, we've got an R value. One question is this R, this correlation coefficient, indicating a statistically significant association between T1 and T2? So first of all, what we're seeing kind of makes sense. If you're slow at T1, you're probably slow at T2. That's why we have this upward trend. And so in order to see if it's a statistically significant association, what we can do is go online and go to a p-value calculator that will tell us if this is a statistically significant association. And when we do that, we need a couple of pieces of information that you might want to write down. So you're going to need R, which is 0.54827, and you also need to know your sample size. And so if you look at your sample size, there's different ways to get at this, but I'm just going to click down, run down, and you can see it's keeping account. I've got a total of 302 X and Y pairs. And so I've already pulled this up. Let me show you how I pulled up this site. This site is basically from social science statistics. It's a p-value for Pearson R calculator. And so this is what we want. And if you go to Google and type in something like Pearson correlation Pearson correlation coefficient critical value calculator, and do a search, you'll get various things back. Here's a Math Cracker site. It works a little differently. We're going to use this one. And so this is this one down here, Pearson correlation coefficient calculator. Whoop. Quick p-value from Pearson R. So we're going to this site. And when we put it in, it wants to know a couple things. It wants the R score. So the R score is simply, what was the correlation coefficient? And remember here it was 0.54827. And then what was our sample size? It was 302 pairs of X and Y values. Remember, X is T1, Y is T2. Significance level. Well, we test things at a significance level where alpha is 0.05, and so that should be 0.05. And then you just hit calculate, and it gives us the result down here. And this p-value is highly significant. It is less than 0.00001. And so it's a statistically significant correlation. And so we can use, instead of just the word association, which is a little vague, we can use the word correlation, which gets at the linear association between X and Y. So we have a statistically significant correlation. Now just to kind of illustrate what would happen, let's say we had an R value which is close to 0. If it was exactly 0, if you remember from what Dr. Beckman said, a correlation coefficient of 0 means that there's no positive relationship between two variables, no negative relationship, that basically your data look like a shotgun blast where there's no pattern at all evident. And so if we do that, what we find is the p-value is 1 because the data are perfect for indicating that there is no statistically significant association. It tells you right here, the result is not statistically significant. But what about a smaller R value, like an R value of 0.15? If we hit calculate, then the result is statistically significant. And 0.15 is a low R, but because we've got over 300 participants here, a big sample size, it turns out to be statistically significant. Sometimes things have some statistical significance when you've got big sample sizes, but they're not particularly biologically significant or important. But our R value in that case was statistically significant. So you can always find this if you look up online that particular p-value site and calculate it.